In this video, we're going to try to get a graphical sense for what we mean by the derivatives or the velocities if we're imagining a vector-valued function like r defining a trajectory. So we're going to start with our example here with the position defined by t and t squared for the x and y components. And we saw earlier that the velocity vector in this case here would be defined by the derivative of time with respect to time, so just 1, and the derivative of t squared, which would be 2t. And so if we're at a position defined by this function, we can get a velocity at that same instant, courtesy of the derivatives. So what we're going to see in MATLAB is a simple plot to start with of the trajectory itself. This is the path traced out by the trajectory. We're going to have to figure out which direction it's moving in from context. But that's actually going to be highlighted when we pick an individual point and we draw a vector at that point with the velocity. That'll actually tell us the direction the particle is traveling in. Now, the way we're going to do that in MATLAB, again, MATLAB is not tested in the course, but it's a useful tool to have. We're going to draw the velocity vector as a little arrow. Quiver is the MATLAB command for drawing an arrow. And if you look at the components here, we see our t and t squared. So this is going to be our position where it's rooted. And then the next two components you see are the 1 and 2 times that time value, so 2t. This is going to be our velocity. So we're going to have a vector drawn at a position, which is the root, and this is the actual arrow. Let's see that in practice here with our MATLAB code. What we see is our trajectory traced out, and when we focus in on time 0.5, which gives us an x of 0.5, we see this velocity vector built off of that. So just from that one picture, we can infer that the trajectory is taking us down and then back up along this curve as time increases. We also notice that without any effort on our part, the velocity vector is tangent to this curve. We'll zoom in a bit here. And that's actually something that has to be true, because as a particle is moving, if we take the displacement on smaller and smaller time intervals, if we zoomed in on a region, it's going to look more and more like a straight line, and that's going to define the direction of our velocity. If we then look back at our animation code, you can see some similarities here. We won't go into the details, but we can see that we're going to plot our curve and then do a quiver of the xy position for the roots and the vx and vy for the velocities. And you can see both of those calculated using t and t squared and the 1 and 2 times t from the by hand calculus calculations. So let's see that played out here. There we are. So there's our location and time. We can see the traversal of that point through space. And at each instant, we have our velocity vector. And you can see that it's changing length. That's about the speed. And that corresponds also to how quickly the dot is moving. We're going to run that one more time just for thoroughness, and just because it's fun to watch. We can see that the particle actually does slow down a bit in sort of a visual sense as it approaches that vertex. And that corresponds to a smaller length for the velocity vector, a smaller magnitude of the velocity vector, which means lower speed. And then it speeds back up as it reaches this other arc of the trajectory. So what we get from this is that all of the calculations that we're doing have an interpretation in a graphical sense. And often the graphical sense is what we're trying to wrap our heads around, and the calculus and the algebra that we do on paper just helps us to understand that in a more quantitative way.